A journey to the center of the Earth, where temperatures are a searing 13,000 degrees Fahrenheit, hotter than the surface of the sun. The most powerful force on the face of the planet, moving whole continents, creating mountains, exploding them apart, and an unimaginable winter of ice lasting 100,000 years. Some of the greatest discoveries in the history of science have revealed what an incredibly complex and dynamic planet we live on. Discoveries that opened our eyes, changing how we see the sky above and the earth below. In March 1980, geologists detected a series of small earthquakes here, beneath Mount St. Helens in Washington state. It was a signal that the long-dormant volcano was waking up. Finally, on the morning of May 18th, it did. Mount St. Helens erupted with a force 500 times the atomic bomb that was dropped on Hiroshima. A cloud of hot ash roared 15 miles into the atmosphere. "230 square miles of forest were wiped out, 6 million trees, enough wood to build 300,000 two-story houses." Throughout recorded history, civilization has lived with the threat of earthquakes and volcanoes. But the cause of their destructive power remained elusive, shrouded in mystery. It wasn't until our first great discovery that a picture of what was happening inside the Earth began to emerge. For centuries, most of what we knew about the Earth's interior came from mining operations like this one. It wasn't until scientists began using seismographs to study earthquakes that they gained a more accurate understanding of the inside of the Earth. When an earthquake occurred, seismographs measured the speed and intensity of seismic waves that vibrated underground. Using this method, scientists identified different layers inside the Earth, each one characterized by changes in rock density. For example, the first layer was the crust, a skin of rock covering the planet. Its depth varied from 3 to 30 miles. Below that was the mantle, with a depth of about 1,800 miles. As for what was below that, a breakthrough discovery provided the first clue. In 1906, British geologist Richard Oldham was analyzing seismograph readings caused by a large earthquake when he saw something odd. As the vibrations from the quake reverberated, they did not arrive at the center of the Earth as expected. It was as if they'd hit an obstacle. Oldham realized the obstacle must be the innermost part of the Earth, a dense mass hard enough to have deflected the seismic waves from going all the way through. Oldham had discovered the Earth's core. It was a landmark discovery because it set the stage for the work of another scientist who was about to help revolutionize our understanding of what was happening inside the Earth. With Oldham's discovery, many believed the picture of the Earth's core was complete. But in the early 1930s, Inge Lehmann wasn't so sure. Lehmann was a Danish seismologist who worked extensively in Denmark and Greenland, studying the velocity of seismic waves from earthquakes. In 1936, she was analyzing the seismic waves from an earthquake that had occurred several years earlier. Seismological stations around the world had made recordings of the same quake. By comparing their readings, laymen calculated that as the seismic waves had passed through the Earth's core, there was a change in their velocity, as if they had encountered another boundary of some kind. Then it occurred to her. Something was missing from the accepted structure of the Earth's interior. The Earth didn't just have one core, it had two. The core that laymen had found was the Earth's inner core. Today, through precise seismic measurements, we know that it's made of solid iron. Solid because gravity at the center of the Earth creates a pressure 3 million times the pressure it exerts on the surface. The core that Richard Oldham had discovered turned out to be the Earth's outer core. It's made of liquid iron and other elements, a hot churning mass that generates electric currents, which in turn create the magnetic field that protects the Earth from dangerous cosmic radiation. Together, the two cores that Oldham and Layman discovered form a massive structure over 4,000 miles in diameter, slightly larger than the planet Mars. At the center of the core, the temperature can be as high as 13,000 degrees Fahrenheit, which is 2,000 degrees hotter than the surface of the sun. To get a better understanding of what we've learned from the discovery of the Earth's two cores, I caught up with Dr. Katherine Johnson, a professor of geophysics doing field research at a mine location in Southern California. What made the Earth hot in the first place?
The Earth's original heat actually came from how the Earth formed. It formed through collisions of smaller bodies, we call them planetesimals. The collision of those bodies released huge amounts of heat that gave
coming
the Earth
from astronomical distance.
That's right, just crashing into each other and turning all their kinetic energy into heat.
And so that heat's still here.
And that heat is still here. There's also heat that was released actually during the formation of the Earth's core. So all these bodies came together, they're rocky, they have bits of metal in them. That metal settled within the Earth to form gravity, just by gravity. But the change in its gravitational energy going from near the surface of the Earth to falling to the center actually also released a lot of heat.
Why hasn't the Earth cooled off?
It hasn't cooled off because it actually cools very slowly. That seems perhaps surprising given how hot it is, but its original temperature was very, very hot, and so it takes the Earth is massive, so it takes a long time for it to cool. That's why smaller planets like Mars, even smaller planetary bodies like the Moon, have pretty much cooled off.
But here on Earth, the cooling off of the planet is perhaps billions of years away, thanks to the intense heat of the core, which acts as a kind of natural furnace. What Oldham and Layman didn't know was what else the furnace was capable of, and that's our next great discovery. Germany, 1911. A meteorologist named Alfred Wegener was browsing through some books when something caught his eye. A list of identical plant and animal fossils that had been found on opposite sides of the Atlantic Ocean. Wegener was intrigued. How could the same species have gotten from one part of the world to another? He examined the eastern coast of South America and the western coast of Africa and was struck how the shapes of the two coastlines might fit together. The more he looked, the more links he found. Species of land mammals in East Africa also inhabited the island of Madagascar. How did that happen? Did the animals evolve in both places at once? Or did they somehow cross from one land to the other, swimming hundreds of miles across the Indian Ocean? And then Wegener saw it all clearly. He realized that all the continents in the world had once formed a giant single landmass that he called Pangaea, from the Greek Pangaea, meaning all earth. It was in Pangaea that the plants and animals found on opposite sides of the world had once shared the same home. Then, over hundreds of millions of years, Pangaea had split apart, and its jigsaw pieces had drifted to their present locations. Wegener called his theory continental drift. Wegener wasn't the first scientist to speculate that the Earth had once been dominated by a supercontinent, but he was the first to pull together all the evidence and make a strong case for it. Unfortunately, his peers weren't very receptive. There was no mechanism to explain how the continents might plow through the oceans. Continental drift was just too incredible to believe. As a result, his discovery was largely ignored.
Rust oder Rust Mitzi.
World War II. German U-boats were on the prowl. To track them, the Allied forces developed new sonar methods, and scientists were enlisted to help survey the ocean floor. When the United States entered the war, Harry Hess was a geology professor at Princeton University. But he also happened to be a Navy reservist, so it wasn't long before he found himself in command of an attack transport ship in the Pacific. To help maneuver when coming in for a beach landing, Hess's ship was equipped with a depth sounder. Now, still being a geologist at heart, he used the sounder to measure the depth of the ocean floor whenever his ship was out to sea. Now, what he discovered startled him. Until the Second World War, most scientists imagined the bottom of the ocean looked like this: flat, lined with nothing but sediment. But about 2 miles beneath the waves of the Pacific Ocean, Harry Hess discovered something else entirely. Mountains, like these here in California, with deep canyons and trenches, hundreds of high peaks that we now believe were once active volcanoes, and all of this at the bottom of the Pacific Ocean. Surprisingly, though, the discovery of the Pacific mountain range is not what makes Harry Hess part of our Great 100. Now, we'll get to that in a minute. To understand where all this is headed, I'd like to skip ahead to another event that set the geology world buzzing. For years, oceanographers surveying the Atlantic Ocean had taken sonar readings that indicated there was something down there, something big. In 1953, they found out what it was: a 12,000-mile-long mountain range. They called it the Mid-Atlantic Ridge.
The reason it's so great.
To fill us in, I paid a visit to Neil Driscoll, a geologist at the Scripps Institution of Oceanography.
One of the big discoveries that was made was that there was this ridge of underwater volcanoes that stood high above the seafloor.
How high is a mountain in the middle of the Atlantic?
The average seafloor depths are on the order of about 4,000 to 5,000 meters. The mid-ocean ridge sits up at about 2,500 meters. So they sit about 2.5 kilometers on average higher than the surrounding seafloor that's shown here in the deep blue colors.
So that's over a mile high.
Yes.
Right? And that's where Harry Hess comes back into the story. Analyzing core samples and sonar readings from around the Mid-Atlantic Ridge, Hess made an astonishing discovery, a phenomenon almost beyond comprehension. The age of the Atlantic Ocean floor, he determined, was progressively older the further it moved away from the ridge. Harry Hess had discovered that the seafloor was spreading. He concluded that molten rock was being forced up from inside the Earth at the ridge, where it then formed into new crust on the ocean floor. Gradually, it was pushed away on either side as more molten rock continued pushing up from behind it. Hess called his great discovery seafloor spreading.
Harry Hess was in a position that he could bring it all together. Things were spreading apart and new Earth was being generated. But if you did this for long enough, the Earth should grow. And it doesn't.
The Earth doesn't get any bigger.
No. Harry appreciated the fact that if new Earth was being generated in one area, they have to be consumed or recycled in another area.
The process that recycles the crust of the spreading ocean floor back inside the Earth is called subduction. But as our next great discovery revealed, it's all part of a much larger process, perhaps the most powerful force on the face of the Earth.
That the earthquakes
Hess's discovery that the seafloor was spreading rescued Alfred Wegener's idea of Pangea from obscurity. Now there was a geological mechanism to explain continental drift. That's simple.
Once you hear it, it sounds great.
It does sound great. By the 1960s, both ideas were synthesized into a single theory, the science of plate tectonics. A great discovery that revealed just how complex and dynamic our planet is. Several groups of scientists had concluded that not only is the Earth's crust moving, but the surface of the planet is broken into large, interconnected plates. These plates are constantly in motion, floating on a layer of molten rock in the Earth's mantle. It seems fantastic. I mean, it seems just too crazy. How could the whole world be sliding around? I can see where people were skeptical.
That's right. That's right. But it's the rates your fingernails grow.
That's not very fast. I don't feel a thing.
That's right. Yeah. But cumulatively, it's huge. So here's the thing: is geologic timescales is what makes this so important. Because if you think of it over a year, you move a few centimeters. If you think over millions of years, you're moving kilometers. About 250 million years ago, all the plates were together in Pangea, and they're moving apart, and they will come back together again.
Why do they move back together?
Because the Pacific Ocean right now has subduction all around it, and the plate is actually being consumed and recycled, where the Atlantic Ocean is spreading without much subduction. So the Atlantic Ocean is going to grow, the Pacific Ocean is going to close, and then we'll start getting closer to Asia and closing up the Pacific Ocean.
It's crazy.
It's pretty great.
Crazy.
And once you hear it, it's hard to imagine geologists not believing in it. So once the theory and the mechanism, that was the important contribution.
Because no one would believe it till they had it.
That's right. So the plates are spreading, they're not plowing.
The understanding of plate tectonics has given scientists new insights into the changing face of our planet. A dynamic example of some of those changes can be seen here on the California coastline, where two of the Earth's largest plates, the Pacific and the North American, collide.
There's a number of results, but one, we get volcanoes where the plates are subducted back into the Earth. These volcanoes happen because the plate that gets subducted releases water, and this water lowers the melting temperature of the overriding plate and makes it easier, and we get volcanism.
So that's where you get Mount Whitney, Mount Shasta.
Things like this, absolutely. The Andes are a perfect example of these type of volcanoes. Other places you get the mid-ocean ridges. You get pieces of the seafloor that are 1 to 2 kilometers higher than the surrounding seafloor. These are underwater volcanic chains that stretch the length of these ocean basins. Other places you get large strike-slip faults.
So what's a strike-slip fault?
A strike-slip is when the plates move by one another, okay? And they don't do it without kinks and twists, and so where the kinks and twists are, there can be places that lock. Yeah. And then they release, and they release quickly with a lot of energy or momentum.
Tipping over buildings and so on.
Causing a lot of shaking, yes.
Yeah. But without earthquakes, you never would have found all this stuff, right?
Earthquakes are really important because they've allowed us to define the plate geometries. They've allowed us to define the boundaries.
So what about volcanoes?
Before volcanoes light off, a lot of times there's pre-eruption seismic activity.
Shaking.
Yes, yes. As the magma ascends to the surface, it causes stress, and the stress is released.
Do you see evidence of plate tectonics right here?
Yes. What we're looking at in the sea cliffs, these were deposited, these sediments were deposited about 500 meters below the sea level, and they've been uplifted. So here, we're looking at plate tectonics in our own backyard.
So far, we've explored what several great discoveries have revealed about what's happening inside the Earth. The next discoveries opened our eyes to what's happening above. With so much technology at our fingertips, it seems like predicting the weather should be more of an exact science. But global weather patterns are so complex, so volatile, it's impossible to accurately forecast conditions more than about 2 weeks in advance. Weather has so many variables, it can change quickly, bringing unexpected fury. The energy in a large thunderstorm can be greater than the destructive power contained in one atomic bomb. Enough energy to generate electricity for a major city for months. One lightning bolt can strike with the power of 100 million volts, scorching the air around it to a scalding 50,000 degrees, 5 times hotter than the surface of the sun. But as late as the 1890s, surprisingly little was known about the sky above, let alone how to predict the weather, until our next great discovery. A French meteorologist named Léon Tesseract de Bort conducted hundreds of unmanned balloon flights. De Bort equipped each flight with an array of clock-driven scientific instruments that continuously recorded the high-altitude conditions. There were thermometers, barometers, and a hygrometer to measure humidity. From the information gathered by these instruments, de Bort was the first to discover that the atmosphere is divided into layers, each characterized by distinctive meteorological conditions. The first layer he found rises from the surface of the Earth to an altitude of about 10 miles. He named this layer the troposphere, meaning sphere of change. This is where clouds form and all our weather happens. Much of it delivered to us courtesy of jet streams, which can hit speeds of up to 200 miles an hour. Above that, de Bort found a second layer which he called the stratosphere, meaning sphere of layers. It reaches 30 miles above the surface of the Earth. De Bort's discovery revolutionized our understanding of the atmosphere and helped usher in the modern science of weather and climate studies. Right now, there are 17 international satellites orbiting the Earth, tracking the weather. Over 1,000 weather balloons are launched every day, and more than 10,000 observation stations monitor climate conditions on every continent. Why all this attention to the weather? Obviously, a timely storm warning can help save lives, but it's also about the economy. In the United States alone, 1/3 of the economy, about $2.7 trillion, depends on our analysis of what's happening with the weather. And de Bort's hot air balloons helped lead the way, just like our next great discovery. In the early days of the 20th century, scientists found that a mysterious form of radiation was spoiling their experiments. They couldn't figure out where this radiation was coming from until a physicist named Victor Hess made an important discovery. Believing that the radiation might be coming from the sky, Hess made a series of flights in a hot air balloon, collecting data with a variety of instruments, including an electroscope, which measures radioactive charge. During one of the balloon flights, there was a total solar eclipse. When the radiation levels stayed the same, Hess knew that the radiation couldn't be coming from the sun. It had to be coming from the cosmos. With that insight, Victor Hess discovered cosmic radiation, electrically charged atomic particles, protons mostly, radiation from deep space, powerful enough to penetrate the Earth's atmosphere, and potentially dangerous too, capable of causing genetic mutations and cancer. It's estimated that each year more than 100,000 people die from cancer caused by the small natural dose of radiation from space. For his discovery of cosmic radiation, Hess, a native of Austria, was awarded a share of the 1936 Nobel Prize. But the prize didn't shield him from the Nazis. Hess's wife was Jewish, and they were marked for internment at a concentration camp. Fortunately, a Gestapo officer warned them, and they fled Austria before they could be arrested. By 1946, they were American citizens, and Hess traded his balloon flights for a series of scientific tests atop the Empire State Building. Instead of testing for cosmic rays, Hess, now a professor at Fordham University, went to the Empire State Building to measure another kind of radiation. Working high above the New York skyline, Hess analyzed radiation levels in rain samples that he collected at the top of the building. The reason is that less than a year before, the atomic bomb had been dropped on Hiroshima. Victor Hess was the first scientist to test for radioactive fallout from that blast in the United States. The origin of cosmic rays is still not clear. They probably come from supernovae, exploding stars in deep space. They may be left over from the Big Bang, where the mass of all the stars in the universe exploded at once. Whatever their origin, we're fortunate that the magnetic field that surrounds our planet protects us from most of the damaging effects of cosmic radiation. But as our next discovery reveals, it's a magnetic field that is continually in flux. As we've already seen, the Earth's magnetic field acts as a shield, protecting our planet from much of the sun's dangerous radiation. But in 1906, a French geologist named Bernard Bruns made a startling discovery about the field. Bruns was examining newly formed volcanic rocks near a lava flow in central France. Lava from a volcano contains minerals from deep inside the Earth. Inside the molten lava, iron particles are free to move. But as the flow begins to cool and form into rocks, the iron particles align themselves according to the Earth's magnetic field, like a compass. They become a fossilized snapshot of the Earth's magnetic field in action. But during his research, Bruns found some of the rocks contained iron particles that were magnetized in the opposite direction. Their compass needle had flipped, pointing south instead of north. This was the moment of discovery. Bruns realized that at some point in the past, the Earth's magnetic field had changed direction and reversed itself. It was a significant discovery. It meant that Earth was a far more dynamic planet than many had imagined, constantly changing. We can see that the Earth's magnetic field has reversed about 60 times in the last 20 million years. That's once every couple 100,000 years or so. And we may be going through a reversal right now because the Earth's magnetic field has decreased in strength about 10% in only the last century and a half. Now, no one's exactly sure why this happens, but Bruns' discovery does raise a provocative question. What happens when the Earth's magnetic field goes to zero? The answer may lie on Mars. Scientists have detected that the red planet once may have had a magnetic field, powered by a furnace-like core, just like the one on Earth. But at some point in its past, the heat source of the Mars core was extinguished. Without its internal furnace, the planet died. Its magnetic field disappeared, and harmful cosmic and solar rays bombarded the planet, wiping out any chance for life as we know it. Could that happen here? Well, the composition and size of the Earth's core is such that the Earth will probably stay hot inside for billions of years. But what happens when the Earth's magnetic field reverses and goes through zero? Well, if it happens in the next 1,000 years or so, there'll probably be humans around, scientists, and they can measure cosmic rays and study their effects on living things. Our next great discovery began with a puzzle. Early in the 19th century, European scientists found that certain rock formations in low-lying areas bore a striking resemblance to rocks normally found at much higher elevations further north. How did they get there? One idea put forth was that the rocks had been moved by giant glaciers that had once expanded out of the mountains, then retreated to their present locations. The theory of the Ice Age was born. What could have caused an ice age to happen? The question remained a mystery until around the First World War. A Yugoslav scientist named Milutin Milankovic developed a theory. At the time, several mathematical models had been developed to explain subtle but significant variations in the Earth's orbit around the Sun. Astronomers had calculated that the distance between the two and the shape of the Earth's orbit gradually changes every 100,000 years. And every 40,000 years or so, the angle of the Earth's axis tilts slightly. This affects where the Sun's energy reaches the Earth. Using these and other measurements, Milankovic calculated, with great mathematical precision, how the orbital variations had caused major climate changes over the history of the Earth. The changes began when a subtle shift in the Earth's orbit produced cooler summers and colder winters. This change created a domino effect that, year after year, century after century, allowed the glaciers to expand and ice sheets to grow. When the orbit of the Earth eventually changed again, the ice retreated. Milankovitch had discovered a mechanism to explain the creation of periodic ice ages. Today, most of Milankovich's theory has been confirmed and accepted. It's estimated that the Earth may have experienced as many as 17 ice ages over the last several million years, with giant ice sheets covering as much as a third of the planet. While periodic ice ages happen over hundreds of thousands of years, our next great discovery has unfolded in just 100 years, which in geologic terms makes it a catastrophic event, more significant than an ice age. And it's happening right now. This is the National Climatic Data Center in Asheville, North Carolina. Weather records from around the world are stored here, some dating back as far as the 1700s. But it's the weather of the last century that's of particular interest to experts like Tom Carl, director of the center. The records indicate that over the past 100 years, the surface temperature of the planet has increased about 1 degree Fahrenheit. That may not sound like much, but many believe it represents a significant warming trend in a relatively short period of time.
The impacts of that warming are indeed substantial. This is a major global problem.
Speculation about what's causing the Earth to heat up has long centered on the burning of fossil fuels. While carbon dioxide and other gases occur naturally in the Earth's atmosphere, scientists wondered if a buildup of industrial CO2 could be responsible for the climate change. Finally, American geochemist David Keeling set out to measure just how much carbon dioxide might be up there. In 1958, Keeling took air samples 2 miles above the Earth, high atop Mauna Loa in Hawaii. The location was chosen because the air was mostly unpolluted. Keeling collected the samples in flasks and measured the CO2 levels with an infrared gas analyzer. The results were astonishing. Keeling found that the level of carbon dioxide in the atmosphere was increasing at a rate of 3.3 billion tons a year. It was a landmark moment. Suddenly, the debate over a connection between global warming and rising CO2 levels became more than an academic issue. Here were measurable data. Today, the level of CO2 in the atmosphere continues to rise. It's now at a level some 30% greater than what experts believe it was prior to the start of the Industrial Revolution. An increase that many scientists believe is having a significant impact on climate around the world. One of the most visible examples of climate change from global warming is here at the South Cascade Glacier in Washington State, where the ice is melting. This is how the glacier appeared in 1928, 1975, 2003. According to surveys, the South Cascade Glacier has retreated by 1.2 miles over the last century. It has lost the equivalent of 72 feet of water from the thickness of its surface. And glaciers are shrinking worldwide. One geological survey of 160,000 mountain glaciers and ice caps reports that the volume of ice is decreasing at a significant rate. While there is a general consensus among scientists that the Earth's climate is becoming warmer, there is still some debate over how much carbon dioxide is to blame. Regardless of the debate, researchers are tracking global warming more than ever. Computer models have been developed to anticipate what may happen if the current warming trend continues, from widespread flooding to the devastation of ecosystems around the world. Volcanologists estimate that the 1980 eruption of Mount St. Helens released about 10 million tons of carbon dioxide into the atmosphere. That sounds like a lot until you compare it to the 26 billion tons of CO2 that humans pump into the atmosphere every year, mostly from burning fossil fuels. Think of it this way. It would take 7 volcanoes the size of Mount St. Helens erupting every day of the year to equal the amount of CO2 emissions that we produce. From the creation of ice ages to the effects of global warming, the Earth's climate is a roller coaster of change. And our next great discovery helped put it all into perspective.
For centuries, people believed that the Earth was shaped by catastrophes, like the biblical flood. But in the early 1800s, an Oxford-educated lawyer named Charles Lyell shattered that belief and revolutionized geology.
Lyell spent years traveling the world, studying an overwhelming number of rock formations and fossil samples. He had a brilliant eye for detail, and piece by piece, he began to see that the rocks told a different story. While catastrophes such as volcanoes, earthquakes, and floods occasionally affected the planet, the greatest changes were the result of an incredibly slow and natural geological process, a process driven by wind, water, erosion, and the heating and cooling of the Earth. A record of those changes was contained in the layers of rock. But here was Lyell's most radical insight. The mechanism for that slow process of geological change was time, lots of time. The Earth, Lyell argued, was far older than was generally accepted, and he presented proof of his findings in a landmark book called Principles of Geology. Today, its publication is considered the birth of modern geology. Sam Bowring is a professor of geology at MIT.
I think very important in Lyell's development of thought was a trip to see the volcanoes of Italy, and Vesuvius, I believe, in particular, where he actually saw that the mountain was built up of successive flows, and they had some of these, they had a good idea of when they were erupted because they were historic, and he was able to use that to extrapolate that the volcano itself must be hundreds of thousands of years old, and at the time, talking about hundreds of thousands of years was revolutionary. Others argued for a directionality in evolution, that the Earth on day one is not the same as the Earth today. Some secular change has occurred, and this is a debate that geologists have today. Were plate tectonics operating 4.5 billion years ago, or is it something that developed later on in Earth history?
Today, many consider Charles Lyell to be the Charles Darwin of geology. In real life, the connection between the two men was significant.
Darwin took the first edition copy of Volume 1 of Lyell's treatise on his cruise with the Beagle. And what he realized from reading this, as he was also simultaneously worrying about evolution, was that here was the solution to evolution. We had limitless time.
Lyell's discovery set off a firestorm of interest in determining the true age of the Earth. Until then, most everyone believed that the planet was young. But with the publication of Lyell's seminal book, geologists wanted to know how young. Our next great discovery provided an answer. Exactly how old was the Earth? The question persisted until 1907, when American chemist Bertram Boltwood discovered a way to make the rocks and minerals of the Earth provide an answer. Scientists already knew that rocks contained naturally occurring radioactive elements, such as uranium. They also knew that each element decayed into other elements according to its own rate or clock, and that rate almost never changed. While studying these rates of decay, Boltwood found that mineral samples of uranium always contained traces of lead. It was an indication he believed that lead was the last element remaining from uranium's slow process of decay. From this observation, Boltwood put it all together. If he measured the amount of lead contained in a uranium sample and calculated it by the known rate at which uranium decays, he could determine the approximate age of the rock. It was a breakthrough discovery. Suddenly, scientists had an extraordinary and accurate new tool for calibrating the geological history of the Earth. It was called radiometric dating.
The great thing about radiometric dating is that it allows us to determine the age of the rocks in the Grand Canyon with quite a bit of precision, so that we can understand the whole history of deposition of these rocks before the canyon was carved. We know that the rocks in the very deep part of the canyon are 1.7 to 1.8 billion years old, and yet they're overlain by a flat surface of sandstone that's only 530 million years. So without geochronology, we would never know that we're missing more than 1 billion years of history across that surface. Now, other places in the world have that history. Here we don't have that history, and that's the important thing to remember. The geologic record is remarkably incomplete.
So a century ago, geochronology, time in the Earth, a century ago, what was it, an accuracy of 10%, 50%?
100 years ago, we didn't even know what we were dating, so uncertainties were much, much larger. They were getting dates of around 2 billion, which, of course, was a huge breakthrough in terms of understanding how old the Earth was, but it was only half of the true age of the Earth. And it really wasn't until the 1950s that people began to date meteorites that we began to realize that the Earth was probably 4.56 billion years.
To appreciate how much time that is, consider this. If we compare the entire history of the Earth to a span of 24 hours, 1 million years would go by in about 30 minutes, which means that the entire epic story of human civilization would be over in less than 1 second. Not even a tick of the clock.
So why is this so important?
When we look at the history of evolution is punctuated by incredible extinction events. The Permo-Triassic extinction 251 million years ago killed 90% of everything that lived in the oceans. So the question is, was this sort of a gradual process where we saw increasing amounts of extinction, and then finally the last hurrah, or was it catastrophic? Was life wonderful on the Permian Earth, and then suddenly everything went extinct? The way to answer that question is through high-precision geochronology. And the data that's accumulating right now suggests that it was an extremely rapid event. So as soon as you say a rapid event, the one model we have that works very well is impact of an asteroid. And recently there has been some evidence put forth that suggests there may have been an asteroid at that boundary impacting the Earth. The other aspect of extinctions that's really important, and to some people even more exciting than understanding the extinction itself, is what happens to the ecosystems. How long do they take to recover? When you wipe everything out, it's like resetting the whole evolutionary clock, and then you allow new things to fill the ecosystems that were completely obliterated. It could be that if it weren't for that extinction, we wouldn't have seen the rise of dinosaurs and then mammals. We could live on a very different planet. We wouldn't live here.
You look at this view and you feel like an insignificant speck.
Right.
And the grandeur of it is astonishing, but then when you think about what you can learn from it, then it's a whole nother level of...
It is. And it's like a book. There's lots of information there waiting for us to extract it, information that we haven't even thought about asking the rock record to produce for us. So there's a lot to do.
Well, that's job security for science.
Yes.
The Earth is a complex and dynamic planet. The crust is shifting, the mantle is moving, the atmosphere is constantly in flux. All the species that live on the Earth are changing along with it. Our ancestors did, or we wouldn't be here. The Earth challenges all living things, and so far, life has been up to the challenge.